pre-calculus students. Today we have an exciting new chapter for you. Chapter 5.4, Common and Natural Logarithmic Functions. We'll start with the common logarithms. So I really like to connect logarithms to exponentials because logarithms are essentially inverse functions of exponential functions. So if we start with the exponential function f of x equal base 10 to the power of x, we'll just get a few points like 0, 1, 1, 10, 2, 100, negative 1 would be 10 to the negative 1 power, which is 1 over 10, and then negative 2 would give us 1 over 100. So if we just put those points on a graph, and connect the dots, we get a lovely looking exponential function right here. So this is our f of x equal 10 to the x graph. Now, if we found the inverse of this function by flipping it over the y equal x line, which is the same as just switching the x and y. So for example, this point 0, 1 on our y equals 10 to the x graph would become the point 1, 0. And the point 1, 10 would become the point 10, 1 on the inverse graph. Okay, and so on and so forth. So negative 1, 110 would be 110, negative 1. And it's going to go down towards, because the exponential graph has a horizontal asymptote y equal to 0, then our inverse graph has a vertical asymptote x equal to 0. And we connect the dots, we get this. Now this is going to be our common logarithm function. In other words, it's going to be g of x equals log base 10x, but because 10 is the most common base that we run into, think about our number system, it's all based on 10s because we have 10 fingers to count. So because base 10 is so common, we just, as usual, we want to be lazy and write as little as possible. So when we just write log x with no base written, it's assumed that we are going to understand that that's base 10. And so again, these functions are inverse of each other. That's why we learn logarithm functions right after we learn the exponential functions. And it's really important to connect those two things. Well, for me, because if I can have my log expression and I can just transform it into the exponential, anytime I get stuck on a log problem, if I transform it to the exponential version, I usually can figure it out. And the key to remember is the log is the exponent. So log v equals u, when I transform, the base is 10, it's not written. The log is the exponent, so u goes in the exponent spot, and whatever is left is equal to v. So we can use this to figure out some log problems without having to use our calculator if we were to face that. So log 10,000 equals x, I just transform it. Okay, the base is 10, the exponent is x equals 10,000, so that x has to be 4. Okay, I'll do another one. I'm going to go through these pretty quick because I'm going to assume it's review from last year, but if you are having trouble, just pause or slow down the video or ask in class. So log 1 equals x, again, transform it to exponential, 10 to the power of x equals 1, so x has to be 0. All right, another example, log of root 10 equals x. We've got to find x. Again, we're going to transform 10 to, the log is the exponent, so x goes in the exponent spot, equals root 10. And with some thought, we see that, well, root 10 is just 10 to the 1/2 power, so that power of x has to be 1/2. Okay, last example with the common log using base 10, log of negative 2 equals x. So we transform base 10, exponent is the x equal to negative 2. And after some thought, we realize, well, there's no number we can put in for x to get a negative out, so this has no solution. And that's why the log function is undefined for negative inputs. And we're going to see that in the domain and range, which I'll get to next, I think. No, I'm going to do another example. Okay. You guys can tell I record the audio after I do the writing because it's too hard to do both at the same time for me at least. All right, log x equals 3. So then I go transform 10 to the 3rd power. Because again, the log is the exponent, so 3 is the exponent spot, equal to, well, what's left in the log is the x, so x is 1,000, and I'll just highlight my answer there. Okay, 10 to the x equals 52. Well, I can go the other way too. I can transform this into the log version. It's going to be log base 10 of 52 and then equal to the exponent, which is x. I put that in my calculator, I get 1.716 roughly. Okay, and this is where my pen started getting weird on me, so just bear with me here. Okay, now we talked about common logarithms, so now we're going to talk about natural logarithms. So if common logarithms was base 10, the other common base is e, 2.718, goes on forever. That doesn't repeat decimal. It's useful because like last section we learned about compound interest continuously, and it follows a model with base, exponential model with base e. And there's population models and other models that we use in the real world, and they have base e. So it's a useful base. It's probably the second most useful outside of base 10. So let's take a look at that graph real quick. We'll just find a couple points. So the function, we try and graph e to the x. So we just pick a few easy points. When x is 0, e to the 0 power is 1. When x is 1, out comes e, and we put in 2, out comes e squared. Put in negative 1, get 1 over e. Put in negative 2, get 1 over e squared. And we just put those points on our graph, 0, 1, 1e, which e is 2.7, so it's like in between 2 and 3, closer to 3. So e is like around there. And then negative 1, I get 1 over e, which is going to be like about 1/3. And connect the dots, there's my exponential function, f of x equal to e to the x. Okay, so to get the inverse function, we flip over the y equal to x line. So 0, 1 becomes 1, 0. 1e becomes e1. And that's probably enough, so we can connect those dots. And there's our inverse function, and this is going to be the natural log function. So we'll call it g of x equals log base ex. And again, because us math people, we're lazy, so we don't want to keep writing base e all the time, so we just abbreviate it as ln of x, which stands for the natural log. Natural because base e comes up with like certain population growth models, and so it's like found in nature a lot, so that's where natural comes from. Okay. Anyways, you don't need to write that base e, just write ln anytime you want to write log base e. Okay, now we'll do a few examples. Well, first I'll do the conversion. So if I have e to the u equals v, where u and v are just some numbers, the conversion would be ln, because that's log base e, v equals the exponent, which is u. Because remember, the log is always equal to the exponent. So that's what the transform looks like. It's the exact same thing as the one for common log. It's just that we use ln if it's base e instead of log for base 10. All right, we'll do a couple examples solving logarithms without having to use our calculator, because, I don't know, it's probably not that useful, but still. All right, so ln of e cubed equals x. So I just transform base e to the x equals e cubed. So x is 3. All right, I'm on fire. Whoopee for me. All right, the next one, next example. So that was example A. Example B, ln natural log of 1 equals x. Pause, think if you can figure it out. All right, so I would transform here. So e to the x, because the log is equal to the exponent, equals 1. And after some thought, x has to be 0 for e to the 0 power to be 1. Box that answer. All right, last example, ln of x equals 4. I'll just transform base e to the exponent 4 equals x, and I just put that in my calculator, and I would get 54.5982. All right, so that's working with the natural log a bit. To close out our discussion of the logarithm functions, let's examine the domain and range of these bad boys. So, good old domain, what are the inputs, what can you put into the function, and range, what are the outputs, what comes out. All right, well, let's tie it back to what we know about exponential functions. So here's the exponential function, f of x equal, let's just use base 10, keep things simple. Well, what's the domain of this function? Stop and think. Right, you can put any x into this. So domain is going to be all real numbers, just as you thought it was, right? Of course. And the range, well, you can't get 0 or any negative number out of this function. So the range is going to be all function values f of x that are strictly bigger than 0. Because again, we have this horizontal asymptote y equal to 0. Because as x gets really large in the negative direction, you're going to get 10 to the negative billion, and that's going to be 1 over 10 to the billion, which is going to go to 0. So it's an end behavior asymptote on the left-hand side of the graph. On the right-hand side, of course, it goes off to infinity. So if we look at the log function, g of x equals log x, base 10, looks like this. Well, stop and ask yourself, what's the domain and range? Well, you can read it off of the graph. One thing to note is the asymptotes are going to flip as well. So on the exponential function y equal to 0 as our asymptote, it becomes the x equal to 0 asymptote on the log function. So you can't put in any negative numbers into this. So domain is going to be the x's that are bigger than 0. And however, we'll get all possible outputs from the range, and it's all real numbers. And if you remember about inverses, inverse functions have the domain of the original is the range of the inverse, and the range of the original is the domain of the inverse. They kind of do a flip-flop, little flippy-floppy action there. So if you remember that, you could just figure it out right away without looking at the graph. Okay. Last example, I'm going to do a graph transformation where I start with the basic natural log graph, so g of x equal to ln of x, and I'm going to need to graph a function that's a little more complicated than that. So h of x equals ln of 4 minus x plus 2. So we recognize that this is h of x is based off of the ln of x function. We just do some changes to it, some moving it around, some flipping, and I'll walk you through that. And we also want to get domain and range of the h function. All right, first things first, because ln of x is written with a positive x, I want to write my function with a positive x, so it's just easier to see what's going on. So I'm going to factor out the negative 1 from the inside, so I can just write it as ln of negative parenthesis x minus 4 end parenthesis plus 2. So here I can read the transformation. So the minus 4, remember when it's a minus to the x, you move it to the right. So this is going to move 4 units to the right. That's what that minus 4 does next to the x. The minus on the inside of the function is a flip over the y-axis, right? If you think about it, it's like a horizontal flip or a vertical flip. I don't know, however you want to think of it. Basically, it's going to flip over the y-axis. And then the plus 2 on the outside moves the graph 2 units up. All right, so the way I like to do these, I like to start with my base function, in this case ln of x. I like to pick 1 or 2 points, and then I like to do the transformations one step at a time to those points, so that I basically keep track of those points, and that's going to help me with the end graph, my h. So the 2 easiest points I can think of on the ln of x function is the 1, 0 and e1. So I'll just put those on here, and this is my basic ln of x function, so I'll start here. Okay, so now I'll do the transformation. So the first one, the red one, I got to go 4 units to the right. So I'm going to take 1, 0, move it 4 units to the right, it becomes 5, 1. And I take e1, and that becomes 5 plus e, not 5 plus e, it's 4 units to the right. So 4 plus e, which is like, e is 2.7, so 4 units to the right plus 4 would be 6.7 roughly. Okay, so it's 6.7 now, and 1. So I keep track of that point. Okay, so this red piece is, I've done that first transformation. I moved it 4 to the right. Oh, this is important, right? Any left and right and up and down is going to shift your asymptote. So my x equal to 0 vertical asymptote now shifts 4 units to the right, so it's an x equal to 4 asymptote. All right, now I do the next one, flip over the y-axis. But the thing is, flip over the y-axis we meant that when it was in its original position, but we really mean it's going to flip over its asymptote, like from right to left. So because the asymptote moved to x equal to 4, I'm going to flip it over that x equal to 4 line. So 5,1 becomes 3,1 when I do that flip, and 6.71 becomes, let's see, if I flip that over, it's like I went 2.7, so it would be like almost to 1 basically. So it would be 1,1, kind of. Okay. So the blue is I flipped from right to left, basically. That's the blue part. And then the final part, I got to shift it 2 units up. So the 0.31 becomes, or the 0.30, I'm sorry, was I calling that 3,1? I was. That 0.30 shifts up 2, so it becomes 3,2. And the point, like 1.3 e becomes, basically you put it up 2, and it's getting a little messy, but it's okay. You could just, a rough sketch is fine. So then the green is the blue graph shifted up 2 units, and I'm done. And I can just read the domain from the graph. The domain is any x's less than 4, and the range is all real numbers. And that'll do it for the logarithm function section. Thank you. I'll see you in next class.